So we're starting the second part of calculus here, which is titled integration. It is a breaking point from what we've previously done. We spent a lot of time doing derivatives, and before that we also worked on limits. And then, outside of the mechanics of those two things, we started talking a lot about the theory, the theoretical ideas that derivatives could show us. And that I don't know, whatever the right word is, but that, reached its zenith, I guess, with being able to sketch a curve, because we could use the second derivative test and the first derivative test and all these things to give us a bunch of information about what a function is actually doing. So I know it got pretty thick with all that theory, and I know you probably feel a little bogged down by it. So the good news, if you do feel that way, is that if you feel comfortable with just limits, and you feel comfortable with actually taking functions and finding the derivative with those functions, applying the product and quotient rule and chain rule, etc., then this is kind of a new subject in a way. We do need to know those two things, but we will venture kind of what I keep in my mind is we're going in the other direction now. And so there will be new theorems. Things will still be related, but this is kind of a new subject. If you have not read this page yet, you should, because this is the introduction to the new ideas that we're going to do. So if you haven't, go ahead, pause, take a quick read of this page. And so one of the things, if you read this page, I think it's a good, nice little introduction. Here's the main thing that we're talking about. How do we find the area of a region bounded by two curves? Okay, so then the answer is integration. And then they say, it's a big deal. Okay. Integration is taking the antiderivative of something. And that's how our connection between these two ideas is going to come about at the beginning. So when you integrate, right, you're finding the antiderivative, just like when we differentiated, we found the derivative. So then there's some big ideas, right? This is a whole chapter preview, so don't get intimidated yet, but we have something called the fundamental theorem of calculus that we'll touch on, okay? They talk about the antiderivative being a process that undoes differentiation. Right, we'll understand why finding the area of regions bounded by graphs is important to calculus. There's something called accumulated area that is going to do a lot for us. So again, please make sure you read that. But today we're doing something pretty, a nice little ease into this whole idea. All right, so we're going to first start off by defining antiderivatives here. Okay, so I'm just going to go over this with you. The notation is a little weird to get over, and you're going to hear me say that a lot during this chapter. The concepts aren't super hard to me. I think it's the notation that gets confusing. But let's just see what notations they're going to be using here. So goal differentiation, of course, is to find the derivative, and we notated that as f prime for some function that we started with f, right? So we'd have this f, take the derivative, and we notate it with the little prime up there. Okay, so when we go in the other direction, we're going to call that the antiderivative, or the process is called antidifferentiation. Okay, and so we're saying we got this f function that we started for before, but instead of taking the derivative, we're going to go backwards. And when we get done with that, we will have a function that we're going to notate as big F. Okay, and so if we take the derivative of big F, we're going to have kind of like what we would usually start with. Okay, so again, what I just said is notated here. The derivative of our big F is now F. Now F, the big F, will be the antiderivative. So we won't know that we will start with this, the little f, and go to the big F. Okay, so okay, so what does that mean? Okay, so let's look at like an example here. So let's say we have this big function, and let's just say that it's x squared. So of course, if we took the derivative of this function, it would be 2x. So then what we're saying is, or at least what the notation is telling us is, if we start with this function 2x, and we want to take the antiderivative of it, and we'll talk about notations on how to notate that you want to do that. But right now, what we're saying is if we start with what we're usually looking at, 2x, and we take the antiderivative of it, we're going to go to x squared. Okay, and that's all they're talking about here, right? An antiderivative, the definition, a function, the big F, is an antiderivative of f, little f, provided that the derivative of big F is that f. Okay, and so that's what I'm trying to show over here. Okay, so then they start off and they say, well, let's, like, all you're doing is just thinking backwards right now. Okay, so this is a little bit of trial and error at the beginning. Okay, and so you're welcome to read this example. It's, I just pulled it right off of trying to explain it. But what I want to point out before we look at the first theorem is that they come up with a constant c. And so this is going to be a big deal. And so we need to notate that, because if you think about, and c is going to be a constant, if you think about taking the derivative of a constant, it is 0. And so how that applies to kind of what we were saying over here is, if we start with this function down here, and we say, okay, well, I want to take the antiderivative of that, then I'm going to go to here, right? It's going backwards, kind of what I was describing here. But we got to add this constant. Okay, and so that the reason of that is from our original definition, that the big F is only an antiderivative if, when we take the derivative of it, we get the other function. Okay, so if we're taking from here, let's start from here. If I want to find big F prime, okay, so I take the derivative of the variable term, and then when I take the derivative of the constant, it's 0. And so then I get to here. So you always got to notate this. And then what we're going to say here is let f be any antiderivative of f on the, okay, so then then all antiderivatives of f have the form of f plus c, okay? And we actually learned that, and here's another connection. We actually learned about this in our last section that we were doing in chapter 4. Okay, and that theorem was 411. And 411, the title is Functions with Equal Derivatives Differ by a Constant. So this is kind of the opposite direction of that. And I think the picture on the next page will make you probably happier than just like reading through it. So let's take a look at that. So if you think about what it means to take a derivative, okay, the derivative is just what? It's just the function that gives you the tangent line at every point, the slope of the tangent line, at every point. And so if you look at these pictures, all of these have the same slope of the tangent line everywhere. All of these, right, every single point has the exact same slope of it, the exact same tangent slope. And so all of these, if we took the derivative of all of these, we would get the same derivative. The only difference is the height. And I think someone mentioned this during class, right? That the height is unknown, and that is true, okay? Because, and this is kind of where this comes into play, right? All of these derivatives would be the same. All the slopes of the tangent lines would be the same. Just how high is it located on our y-axis? Okay, so you do need to include your constant. All right, so now, we're going to develop some rules here on anti-differentiation, but always keep in mind that it's an easy check. Well, at least at the beginning, it's going to be an easy check, right? Because you know how to take a derivative. So whenever you take the antiderivative, all you have to do is take the derivative of what you said you just came up with, and it better be your original part of the problem. And that's what they're saying, that, all they're going through here in this next example, and it's worth looking at, is just to think backwards on it. Okay, so for instance, right, if we start off with 3x squared, well, what the derivative of what gave us 3x squared? Well, if we did our power rules here, right, 3 times x and then 3 minus 1, so 3x squared. So the derivative of x cubed is 3x squared, so therefore, right, the antiderivative is 3x squared. But since we have this idea of like, well, we don't actually know how high it is on our y-axis, we're going to put a plus c in there. Okay, and so likewise with this, it's just the inverse tangent plus c. Why? Because the derivative of inverse tangent gives us this fraction. Okay, so then again, with what you're thinking of on c is the derivative of what gives you sine. Okay, well, the derivative of, and they go through, well, derivative of cosine is negative sine. So in order for us to get to positive sine, we better add a negative in there. So the derivative of negative cosine is sine. Make sure you add your constant of integration. Okay, so now we got a little bit more notation to take care of here, right? We're introducing indefinite integrals. And again, this is no different at all from just taking an antiderivative. We just need a way to notate that. And so they start off and say, remember, ddx of f means take the derivative. So what we're going to do, and I didn't get it on my picture here, is come up with this little curve. Okay, this is an elongated S, and they talk about up here, and you should totally read this, right? They talk about how for historical purposes, there's a reason that it's this shape, okay? And that's because it's an S, and but that's as much as you need to really know about it right now. So whenever you see this little shape, it's telling you take the antiderivative of whatever you're starting with, okay? So when it looks just like an S without any other numbers around it, we call it an indefinite integral. The function that follows it right here is called the integrand, okay? And then the dx they're just saying is, right now they're calling it just the independent variable, okay? So then this is representing what you're taking the antiderivative with respect to, kind of thing. Okay, so again, just a little bit more notation. These line up exactly with the example above. Okay, so they're not going to say find the antiderivative of something. They're going to give it to you like this, and that means find the antiderivative of that. All right, so working backwards is great, but we need some rules about it. Okay, and so let's bring back the antiderivative that they just gave us, right? We have this integral of 3x squared dx, and they're saying, oh yeah, well that's really x cubed plus c. Okay, so let's see the power rule, the way we can write it out. Okay, and again, this is just something that you have to remember, right? And so, right, if we start with this function, right, this function, just like, again, we're just going in the opposite direction. So instead of subtracting our exponent, now we're adding the exponent. Okay, and then remember, when we take the derivative, that number pops out front, right? The 3 comes out front. And so then in order to deal with that situation about to happen, we have to divide by whatever that is. Okay, so not a big deal. All you're doing is adding 1 to the exponent and then dividing by that same number, no matter what else is going on. And then make sure you get your C in there. All right, so we'll do a couple of these and we'll talk about, and we'll go through these theorems and we'll do an example problem just to reinforce it. But I mean, this is like the big deal. Okay, like everything else, basically you just like the derivative rules, you just got to memorize a bunch of stuff. Okay, so not really that huge. Again, when you get to here, you should be able to take the derivative and get to your original. All right, so the constant multiple and sum rules should look very, very familiar. Okay, these are the same as they were with derivatives. And all they're saying is you can always take whatever the constant is being multiplied by your function out front. Now just be careful because you may have to factor something out depending on how it's written. Or as I show in the example below, you can do it to each term. Okay, and so then they're saying that's basically what they're saying with the sum rule. You can have multiple functions added, and then you're just going to break them up. Okay, and then the example they're going to show us has to do with terms. Now, as we kind of look through this real quickly, right, we are understand that you're probably not going to break it up. You're not going to break it up the way they're doing it here. Okay, this is just what is going on and what we're allowed to do. And sometimes it's going to be nice. But like on this problem, you're never going to go through all these steps. But look what they're saying. They're saying, look, we have one big function, but really it's the sum or difference of 3 functions. So we're just going to break it up and take the antiderivative of each of them. And since, maybe you don't want to deal with that 3 right now. And again, once you get used to it, you're not going to worry about this. But you could take that 3 out front. You could take the 2 out front, which again, you're not going to do that. And you take the 5 out front. Okay? And so then we can do the antiderivative of something very simple. And then we can redistribute the things that we took out. Again, this one isn't too big a deal. If you think of your power rule, going from here to here, right? All you're going to do is add 1 to your exponent. That's why it's a 6. And then we have to divide by that number that we just created. We have to divide by that 6. So 3 over 6 is 1/2. And so that's where that comes from. Make sure you understand this, right? If you do have a constant, you would bump it up to the x because the derivative of x is 1. Okay, so that's why this would be a weird move to do because you would just say, well, the derivative, of 2x is 2, so then the antiderivative would be 2x. Don't forget about your constant of integration. So let's look at 2 examples just to kind of drive this home. I'm going to look at 28, and I'm doing these for a specific reason. But again, that symbol there means take the antiderivative of whatever function precedes it. So that was our integrand, okay? And then our variable of integration is going to be m, and that's what that's representing. Okay, so know your limitations, right? We cannot do this as is because we have multiplication. All we know right now is the sum rule. So then that means we have to distribute. So then we're saying that it would be 60m to the 4th minus 50m squared dm. And so now we're working on the product rule. Again, you can break these up if you want, but what is usually going to happen is you're going to say, well, okay, I'm going to leave 60 alone. Okay, I know I'm increasing my exponent by 1, and then I'm going to divide by what I just increased it to. All right, so again, right, so now we're subtracting. So just leave the 50 there, we're going up 1 and then dividing by what we just increased to. Don't forget about your constant. Okay, so then of course you should simplify like you always should. So I believe that is what? So then we're saying 12m to the 5th minus 50 over 3m cubed plus c. Okay, and again, very, very easy to check. Just take the derivative of that. Okay, of course it works with negative exponents just the same, just like we did with our derivative. So, think about those different situations. And then the other one I'm going to do is 36. So this is our integrand. Okay, and again, know your limitations, right? We have no way of handling anything with division yet, so we are going to have to simplify this down. So then we're going to make this into 12 t to the 5th minus 1 over t squared. Again, that's our integrand. Okay, make sure you get used to the notation. And so again, here we go. This is, how I would think about it. So we're going to leave the 12 alone for a second. We're going to increase our exponent by 1 and then divide by what we just increased to. So again, it's easier to deal with this as a negative t to the negative second. Okay? And so then we're going to leave the 1 alone, right? There's a coefficient of 1 there. We're going to go up 1, add 1 to our exponent, and then divide by that same thing. Don't forget to add your constant. Okay, so, again, easy to check. Right? The derivative here, 6 times 2 is 12. Subtract 1, 12t to the 5th. Right? Negative 1 out front. Right? That's where we get our subtraction from. Subtract 1, negative 2. There we go. Simple process. Okay, so the other part I want you to look at is antiderivatives of trig functions. And you actually already know them because you know how to take the derivative of trig functions. So again, this is just a memorization thing. You can look at the proofs if you want, but I do want to point out, what they're saying over here. So, the notation and the words matter is basically what they're saying. Because they're saying if you take the derivative of tangent, you get secant squared. Therefore, the antiderivative of secant squared must be tangent plus a constant. Okay? And then they're saying, oh, well, if we add something in, what if there's something inside? Well, okay, we're going to deal with that on the next page. But they're saying, look, and they're referring to this one, right? Look, the derivative of cosine of 3x is negative 3 sine of 3x. Okay, so therefore, to integrate the antiderivative of negative 3 sine 3x is cosine of 3x plus c. Okay, and take a look at that idea as well. All right, so all they're doing in this section is kind of working backwards, just like we started off on, or in this example, sorry, it's kind of like we started off with the power rule. So let's go to the next page and take a look at what they're actually saying, or what the actual rule is. Okay, so they're making some statements here, and notice that they give us, they give us a multiplication on the inside. So think about like how this works, right? If you were given this statement, find the derivative of sine of ax, where a is a constant, some number, right? Some real number. Okay, so then you'd have to apply the chain rule. So the derivative of the inner, a to the x, would just be a. The derivative of the outer, sine, would be cosine with the inner replaced, right? The derivative of cosine a to the x is the chain rule. Derivative of a to the x would be a. The derivative of cosine would be negative sine, replace the a of x, okay, and so on and so on. So then, again, you can always think about what's going on here, and we will introduce the equivalent of the chain rule. It's called the substitution rule, but that's later. So they're saying you can just use this as long as, right, you're just multiplying, your inside function is just some number in x. And then this is the rule, okay? So remember, we're going in this direction now. We're starting here, going here. So what is the antiderivative of cosine a to the x? Well, right, it's 1 divided by that number that you're multiplying by on the inside. And then the, right, since the derivative of sine is cosine, when we take the antiderivative, now we're at sine. Okay, so you can just memorize these. They're not like, you should have them basically memorized already, right? You just got to know which direction we're going in. And I keep referring to which direction we're going in because, you know, ideally you're often thinking of our velocity and position situation. So really, you know, what we started with is, and we'll talk about more in this later in this section, we start with a position function, go to a velocity function when we take the derivative again and go to the acceleration function. Well, what we're working toward is, what if we start with an acceleration function? Then we can go to the velocity function, and then we can go to the position function as well. So very applicable stuff in the long run. That's why I keep saying in the opposite direction. Okay, so you're going to have to memorize these. Okay, and then they kind of go through some examples. So I'll do one example here for you. Okay, so let's take a look at this one. Remember, you can break this up if you want. You know, the idea is that we can just take the integral or the antiderivative of sine of 4t. Okay, and so then, again, the way this works is whatever the inside number is, this 4, we're going to have to multiply by 1 over that. Okay, so 1 over 4. And then the derivative of cosine is negative sine. And so then we get to there. All right. So now, and I'll write this out, it's always 1 over whatever that number is. And then times negative cosine okay, so to simplify this up a little bit, we're saying the antiderivative of this function is going to be negative 1/4 cosine of 4t plus 4 cosine of t over 4. Okay, so, you know, I think definitely at first, you know, I would write out this kind of thing, right? It's always going to be 1 over whatever this number is here. And so I think it's safer to just say 1 over that and then flip it to there. I'll do one more because just to kind of refresh you on your trig stuff again. I want to look at 42. I did that one to show the what to do when there's a real number being multiplied on the on the inside. So let's look at 42 also. Okay, so again, like I said before, know your limitations, right? We can't handle anything that's dividing. So let's split this up a little bit and see what we can manipulate it to look like. So then we have sine of theta over cosine squared of theta minus 1 over cosine squared. Okay. So I'm going to rewrite, we got to make this into stuff that we know how to do, right? We know all these derivatives, so we got to make it look like something that we've already taken the derivative of. So I'm going to take this first fraction and break it up so that it looks like 1 over cosine times sine over cosine. And then, right, the 1 over cosine squared is really secant squared. Okay, and so then a little more trig stuff, right? We have secant times tangent minus secant squared. Okay, and so remember what we're doing. It's kind of like what the derivative of what gives us secant tangent. Okay, so the derivative of secant gives us secant tangent minus the derivative of what gives us secant squared. Well, the derivative of tangent gives you secant squared. All right, so just a little bit different way of looking at it. Nothing too serious for us to stay on our pace. I would like you guys to take a look at 11. Hold on. 11 through 45 odd. Shouldn't be that bad. And that's on page 347.